All right, a few loose ends to clean up in Chapter 5. I'll just have some hopefully brief comments about these little things, just in case you're wondering in the reading, you want some clarification, whatever. And just some little examples. When they talk about an inverse square law, this works for gravity as well as light. This is pretty much true of anything that gets weaker with distance. You know that if you walk away from a light bulb, it's going to look dimmer, right? If you walk far away from it than if it's pressed, right up against your eye. So, and gravity works the same way. We said that if you get far away from the Earth, the gravity of the Earth, feels weaker. The way that these things work most of the time in the natural world is that they go down according to an inverse square law. And there's a really good reason for that in geometry, but we don't have to go over that right now. I'll just show you how it works. All it means is that if you're really close, you intercept a lot of the light, right? But if you are over here with the same size of detector or whatever, the light gets more spread out. It's not as bright over there because you don't intercept as much of the light. And so the square law means that if this is your distance, if you are 1 unit away, whatever that is, a meter or an AU away from the sun, whatever, then the brightness would be, let's just say 1. It would be 1 amount bright. Anyway, full brightness, right? If I go 2 units away, if I double the distance, then the inverse square law, it says that the inverse square law says that the brightness goes down as 1 over the square of the distance. Okay, so if I go twice as far away, then the brightness is only a quarter as much. Right? It doesn't get halved. It's not half as bright. It's a quarter as bright. You got to square it. If I go 3 times further away, you'll get the pattern. Then the brightness is only a ninth, right? You square it. You square the distance. If I go ... If I go 10 times further away, for example, Saturn. Remember the table that we did earlier. Saturn is roughly, it's 9 point something or other. It's about 10 times further away from the sun than we are. So what is the brightness of the sun 10 times further away? Well, you square it. And so the sun is only 1/100th as bright out at Saturn as it is here on the Earth. That's just the way that light behaves. And that's why in the probes, if you read about the probes that went out to Saturn, like Cassini, they have a finite lifetime. Cassini had to be programmed to die to go into Saturn's atmosphere because solar panels don't work out at Saturn. They don't get enough energy from the sun. And so they had to have a little nuclear reactor with fuel. And when it ran out of fuel, the probe's not going to work anymore. So they got some extra data out of it there at the end. So anyway, this is how the inverse square law works. You just square the distance, and then that is the strength of whatever it is you're trying to measure. The brightness of the light or the gravitational field works out to be the same way. It's only 100th as strong if you're 10 times farther away. By the way, if the Greeks knew this, they could have guessed at just how far away the stars were, because the book also makes the point that if you know, for example, you can work backwards, right? If you know how bright something should be, and then you look at how bright it looks, you can calculate the distance. That's a lot of words, and we'll do that here coming up, maybe next week. I'll give you an example of that. But anyway, the idea is, suppose I know how bright a light bulb is supposed to be, and I notice that when I look at it, it's only 1/100th as bright as I think it should be. Well, then that tells me that I'm 10 times farther away than when it was fully bright, right? That tells me the distance of the light bulb. So this is a way you can work backwards, and if you observe the brightness, you can calculate the distance. That's the idea. So, for example, if you look at a star like in the southern hemisphere, I think the book mentions, I have it written down here somewhere. Oh, Alpha Centauri. That's the star that's one of the stars that's closest to us. You can only see it in the southern hemisphere. You can't see it. It's below the horizon here. But anyway, it's a star that's very much like the sun. If we assume it's exactly like the sun, if it puts out as much light as the sun does, then what we can do is compare its brightness to the sun's brightness and work backwards and calculate the distance, right? We can do that. And it turns out that this brightness is 1 over, I think I've got it written down here, 73
billion.
It's only 1/73 billionth as bright as the sun. You can measure it. You can put a little light meter up to the sun and register how bright it is, and then you have to. It's a sensitive instrument, but you can measure the starlight coming from Alpha Centauri. You can measure the brightness of this thing, and it turns out that it's 73 billion times fainter than the sun. Well, what you can do then is work backwards. In other words, take the square root of that number, and that tells you how much further away it is than the sun, right? That tells you the ratio of those distances. So if we work backwards, you can do this yourself. Take the square root of 73 billion, and what you get is, and then flip it because it's a ratio. So you get 270,000. So Alpha Centauri is 270,000 AUs away, 270,000 times as far away as the sun. That's the right answer. It turns out that star is pretty much like the sun. It gives off about the same amount of light. Notice that we don't always know that, right? Just because a star is dim, it could mean that it's really far away. But also, it could mean, this is something we'll have to work through next week, it could mean that it's a star that just puts out a lot less energy than the sun. Maybe it's close. Maybe the star is dim, and even though it puts out a whole bunch more energy than the sun, it's just crazy far away, and that's why it appears dim. So there's this sort of trade-off between distance and brightness that we have to work out. But this star happens to put out about the same amount of energy as the sun, so we can go ahead and calculate its distance, which is neat. So that's how far away it is, 270,000 AU. That's a lot. And that's one of the closest stars to the sun. It's 270,000 times as far away as the sun. That's really, really far. We'll talk about that more next week. Anyway, that's the inverse square law. Okay, next on our little tour of Chapter 5 is this thing called Wien's Law, and we've talked about it before. The law, all it does is it puts a couple of numbers to Wien's Law. The idea is, and again, we've talked about this before, is that things that glow because they're hot glow with a characteristic temperature. You know this from your heating element on your stove, let's say. You turn it on, and at first it's not glowing at all, at least not in the visible, right? But you can put your hands over it, and you can feel the infrared heat, right? And so that would be over here. Oops, you can't see that. What color is not being used here? Let's say, actually, that's a really good question. I don't know. This color, we'll see. That would be way over here somewhere. So you turn your stove on and you can feel the it's glowing in the infrared, but you can't see it yet with your eyes. You can feel it with your hands. You know the stove is on because you can feel the heat. And then as it gets hotter and hotter, what happens? It starts to glow a dull red color, right? The peak of this brightness. These curves represent the brightness at each color. Right down here is wavelength. So as the thing heats up, it turns out that it starts emitting more and more light closer to the visible part of the spectrum. And so when you come closer to the visible part of the spectrum from that direction, it starts looking red. And so the heating element will start to glow a dull red. And then it gets hotter and hotter and hotter. And now it starts being represented by these curves. Maybe it's this, and maybe it's that, and maybe it's that. So it'll glow a red color, and then an orange color, and then a yellow color, and then eventually it'll glow sort of a white hot. It actually doesn't glow. You look at that and you think, doesn't it glow green at some point? It looks like it should. It kind of doesn't. Because what happens is our eyes sample here, here, and here, and it all kind of runs together and combines to be white. But anyway, as something gets hotter, it starts throwing off more radiation that is shorter wavelength. Wien's law just gives numbers to it. So if these were stars, get rid of all this junk. Here are the curves. These are called, by the way, these are called black body curves. The reason they call it black body is because these represent the radiation that something gives off just because of its temperature. If it was a black hunk of iron, let's say, that it's not paint or anything on it. If you heat it up, it's going to glow with these different colors, even though its color, at room temperature would be black. right? So that's where black body comes from. It just means this is the color it would have. It's the color some sort of black hunk of iron would have just because of its temperature. There's no paint. So these are just called black body curves. So at 3,000 degrees, most of the radiation that this thing is giving off, what color is most of the radiation coming? It's here, but in nanometers, here's the visible range. Here's 400, and then here's 700. So most of the radiation is in the infrared. But look, just a little bit right here, just a little bit is in the visible part of the spectrum, so that's why it looks red, because we're picking up on that little bit. Now heat the thing up to 4,000, and what happens at 4,000? Look, the peak has shifted. There's the peak. It's coming closer to the visible part of the spectrum, and then look, all of this stuff we can actually see, and now you're mixing in a little bit of yellow, a little bit of green, tiny little bit of blue, right? So the overall color, if you mix all those colors together, like our eye does, the overall color turns out to be maybe a little bit more yellowish, a little bit more orangey yellow. And then it heats up some more, and now the peak for something that's 5,000 degrees, the peak is actually in the visible spectrum. And then 6,000 degrees starts to look more and more sort of white hot, because it mixes the peak is in the visible part of the spectrum, and it mixes all these colors together. It's no coincidence, by the way, this happens to be the 6,000 degrees. This is about the sun. And it's not a coincidence that the sun, look, it puts out most of its radiation in the visible part of the spectrum. You should actually think of that backwards. Because it makes sense that our eyes evolved to see in the range where the sun emits most of its light. That kind of makes sense, right? We pick up information about the world where we can see it, so it actually kind of works backwards. If our sun were dimmer, if our sun were 4,000 degrees instead of 6,000 degrees, you might imagine that the animal kingdom would evolve eyes that would see into the infrared part of the spectrum, because we'd pick up most of the radiation over there. Okay, here's the law. Here's what we actually do, sort of like in the lab. What we actually observe is the color of the star. We can actually observe these curves. So if I look at the color of a star, and the color meaning where the peak of these wavelengths, or where the peak of these curves are, the overall color of the star. If I look at the overall color of the star, let me switch back to white. The peak of the black body curve is at a wavelength that's equal to 3 million. It's actually really easy. It's 3 million divided by the temperature. Cool. And what we really do practically is we turn that around, just do a tiny bit of algebra. The temperature is equal to 3 million divided by the wavelength, the peak that we observe. So let's say we look at a star, and I'll show you these next week. It's actually really, really easy. If we look at a star and we look at these spectra, because all these spectra are is just you pass this through one of those diffraction gratings, you smear the light out into a rainbow, and you just see where the brightest point is. So that brightest point is right there, the peak. So it's easy to calculate the temperature of the star. It's really, really simple. For example, if the peak of the wavelengths comes at, let's say, 500 nanometers, sort of a greenish yellowish. If the peak occurs at 500, right in the visible range, 500 nanometers is 500 times 10 to the minus 9. Okay, so what I'm going to do is just plug that right in. How hot is this star? It's 3 times 10 to the 6th divided by 500 times 10 to the minus 9. Cool. Well, you can do that on your calculator if you want. I'm going to, just for kicks, I'm going to change this. I'm going to make it 3 times 10 to the 6th. Can't I make this, if I move that over 2 places, then I increase that by 2, so I can make this 5 times 10 to the minus 7, right, from the first weak. I can do that.
3 divided by 5, that's 0.6.
Let's see, 6 minus 5. Let's see. Did I make a mistake? I made a mistake. 3 times 10 is 3 million divided by.
Oh! You know what's confusing me? I remember. This is already in nanometers. I don't have to put. Look at that. I don't have to put the 10 to the minus 9 there. All you have to do is put this in nanometers.
I just remembered. That's right.
So all I have to do is do 3 million
divided by 500.
3 million divided by 5 times 10 to the 2. This makes a lot more sense. 0.6 times 10 to the 4th. So this is just going to be 6 times 10 to the 3rd.
6,000. Okay. Where did I... let me do that again. Where did I mess up?
All you do is you put 3 million
divided by where the peak is in nanometers. You just read it off the graph, wherever it happens to be, and then you divide those two numbers,
and then boom.
6,000 kelvins is the temperature of the star. That's pretty much the sun. Cool. So that's Wien's law. You just divide 3 million by the wavelength, and then you got the temperature. It's actually a really simple measurement. We do it all the time. You'd think if we did it all the time, I wouldn't mess it up, but I messed it up.
Okay, next.
Types of spectra. All right. We already sort of know this. When
we looked at the, I think I put up a picture of the continuous spectrum here.
And that's when I smeared the light with that diffraction grating. I smeared the light from an incandescent bulb.
This is from a hot, dense source.
Usually it's from a solid or a really dense gas or liquid. You get this continuous spectrum. And what it comes from is lots of atoms jiggling back and forth very, very quickly. The electrons are the things that are jiggling fast, and they emit light all the way across the spectrum. So you just get a sort of a continuous rainbow. When we look at a star, the star itself, turns out that stars are gaseous, but they're kind of a dense gas. And so when we look at it, what the star itself emits is pretty much a continuous spectrum. But when we look at a star, we don't just see that. We don't just see the star.
Look, the starlight
typically has to go through the outer atmosphere of the star. So the cloud of gas in this is from the textbook. The cloud of gas, this might be the atmosphere of the star. Because stars are gaseous, they don't have a solid surface, and that's it, right? They're just sort of a gaseous atmosphere that gets thinner and thinner. So as the light goes through this outer atmosphere, what happens is...
Okay, the cloud of gas itself,
if it were hot enough,
it would produce this. This is what we got from the gas tubes.
This is what we get from a hot, thin gas, right? We saw this, just bright lines and nothing else. But something special happens. If we get the light from a star, if we get a continuous spectrum and it goes through a cloud of gas, there's something neat that can happen. Okay.
Let me set this up. What we had was level 1, level 2. Let me make a little smaller level. Okay. So suppose we had level 1, 2, and 3. Remember, this is our
hydrogen atom.
So here's our proton in the middle.
Not to scale. And we have 1, 2, and 3. Now 2 and 3 should be closer together. Anyway, I'm just going to tell you the idea. Let's suppose in this cloud of gas that it's up to a certain temperature where there are lots of collisions. And these collisions are hitting these atoms together.
And some of these electrons, which are normally at level 1,
right, in a cold gas, the electrons like to stay down at level 1. But around a star, suppose it's hot enough so that there's some of these electrons that are kicked up to level 2, just from the collisions. Eventually they'll decay back down to level 1, right? But let's just say that they're kicked up to 2. Some proportion of them just happen to be at 2 for a little while. Here's what happens.
Notice from this continuous spectrum, included in here is light at
All different wavelengths.
in particular. Suppose
A light of this particular color, 656, suppose this light comes in and hits that electron. What does it do?
that electron is then going to absorb it,
Because that's the exact right amount of energy,
and it's going to kick it up to level 3.
right? Because going from level 3 to level 2 emits 656. That's H alpha. So if 656 hits that electron at level 2, it's got exactly the right amount of energy to kick it up to level 3. So that's what's going to happen. So these
Particular wavelengths right here,
if that's 656, those hit that electron and make it jump up to level 3. And then once it's at level 3, it can decay back to level 2, right? And you're like, well, so what's the big deal? It absorbs the red light and then it emits the red light. But here's the point.
it emits the red light when it goes back down.
It emits the red light in a totally different direction. That's the point. So if the light was coming to us, then it gets filtered out.
And so this is called
An absorption spectrum. So in other words, all the light that has wavelengths that are not the exact right amount to kick that electron up, they just go right through. And we see them.
So we get this
continuous spectrum, right? But at those very special colors that can kick the electrons up, and then they fall back down and emit that light in another direction that doesn't come to us,
we see a blank spot.
we see a dark spot. So
This is called an absorption.
spectrum. We will definitely see examples of this because it turns out this is what we see for basically all stars. We see absorption spectra. So instead of seeing the lines that we saw from the gas tubes, when we look at real stars, what we see is we see sort of the inverse of that, right? We see the continuous background, we see the rainbow, and then we see dark lines. In the books, that's called the Fraunhofer lines because he detected them in the sun. He split the light of the sun up, and he noticed that there were these dark bands in the solar spectrum. He had no idea where they came from, but they were explained later, once we understood atomic structure, as absorption lines. Those are lines that have been filtered out by the atoms present in the atmosphere. So we can tell what atoms are present in the atmosphere not by the emission lines that we see down here, but by what lines they filter, the absorption lines. It's the same idea. It's just one more little level of complication. Okay, so we will definitely see examples of this next week. Okay, one thing left. I wanted to talk just briefly about the Doppler effect because it turns out it's going to be really important for us. Everyone in this state knows exactly what I'm talking about when I put up the picture down there in the lower right. We'll get to it in just a second.
Here's the idea.
If you go to a pond or a pool and you tap on it, you get circular rings, ripples, waves, right? Suppose I do that. Suppose I tap on the surface of the water once every second, except I'm moving as I do it. So
Here's what I'm saying. 5 seconds ago, I tapped on the water.
so there's my ripple, there's my wave.
Here we go.
This was 5 seconds ago. 4 seconds ago, I did it again. But 4 seconds ago, the wave hasn't gone out quite as much.
All right, the wave is a little bit smaller, so let's see if I can do this. 4 seconds ago, I tapped on the water right here. So let me make a circle around that point.
And then the software cleans it up for me. So pretend that's centered.
3 seconds ago, I did the same thing. So now let me make a circle centered on the 3. And you start to get the idea. I think I'm not going to end up doing this very well. 2. Make a circle centered on the 2. And then the 1.
Yeah, well, I didn't do it very well. Anyway, you get the idea. So as I'm tapping on the water and moving, I'm making circles, and the circles don't know that I'm moving, right? The circle, I just tap, and the waves go out in a circle. But the next circle is going to be offset a little bit, and the next one's going to be offset again.
Well, look what the effect is. As the waves are going this way, what is this person, if I have a person over here
Looking at these waves, and the person is measuring the frequency and the wavelength.
Look at the wavelength of these waves. The wavelength here is smaller than for an observer back here. The wavelength is longer. Look at the space between these waves. Right? That's longer. The waves are more compressed
In the direction towards an observer than away. Right?
If the wavelength is smaller, then we call this, for light,
blue shift, because the light is shifted towards the blue.
Longer wavelengths are called a red shift.
So the person behind is going to say a longer wavelength for the same thing, for the same waves, right? The person behind is going to see a longer wavelength than the person that's in the front. This is true for any source of waves. This doesn't even have to be light. It could be sound. You've all heard it. As a car goes by, you've all heard, in fact, the sound effect itself, you know exactly what it is. If I go, right, you know instantly what that is. That's a car going by. Because the frequency drops as it's a little bit high when it approaches, and then the frequency gets lower. The wavelength gets longer as the source recedes. This is true for sound, it's true for water, and it's true for light. So if someone walks towards you, does their shirt look a little bit more blue than normal? It turns out the answer is yes. Are you ever going to see it? Like if someone's wearing a white shirt and they're walking away from you, are you going to be able to tell that their shirt looks red? No, because the shift is so tiny that the eye is not going to be able to discern it. But if you don't believe it's happening, then feel free to travel as fast as you want on the highway, because you're not going to believe that radar guns work. This is exactly the principle behind radar guns. In the police car, they fire microwaves forms of light that are on the electromagnetic spectrum, right, that are too red for us to see. But they fire microwaves from a radar gun at you, and those microwaves bounce off your car and go back. And based on the frequency that goes out and the frequency that comes back, they can tell the little red shift and blue shift, the little machine inside can tell the difference. And the amount of difference, the percentage difference, tells you how fast you're going. The greater the shift, the greater the percentage difference, the faster you're going. And so that's exactly how radar guns work. So this is a real thing used in lots of different circumstances, which brings us to
Tornadoes.
So we've all seen in the springtime, we've all seen weather forecasters go nuts when they see a hook on a storm, right? A hook echo on this thing, because that's characteristic of a tornado. But sometimes it just happens to be what the storm looks like. The definitive measure for whether there is a tornado on radar is they'll go over to velocity data and they'll look at this. And look at this.
Here is, if the radar, let's suppose the radar is up here. This is a part of the storm. The red is a part of the storm that's going
away from the radar,
and the green is a part of the storm
that's going towards the radar. And so what they look for is they look for a really tight pattern
of something that's going away
and close. Because what does that really mean? If you see really tightly together
winds that are going away and winds are going towards, what that's really telling you is that they're rotating.
Right? And a tight pattern of rotation like that means that you have a tornado. So this is Doppler radar. This has been used for years, and this is how they can tell if there's a tornado just based on radar without anyone actually seeing it. So this is what throws all the warnings, is exactly the Doppler effect. One part of the tornado, the little funnel, one part of the funnel is coming towards you, and right next to it, a part is going away from you because it's rotating, and the radar can catch that. And so that's how we can find tornadoes. This calculation, with reference to astronomy, this calculation is how we can, well, we'll see as we go along. We use this constantly. This is how we can tell that galaxies are moving away from us. In the lab this week, I forgot, in the lab this week,
There's a star called Spica. And Spica is really neat.
It's a bright star in the western sky right now. It's a fairly hot star, but when we look at the spectra of Spica, we see something really cool.
Which is, Spica is actually a double star, which is not that unusual. But it's a double star where these stars are so close together
that they're actually egg-shaped. They orbit each other in 4 days, not like a year as the Earth goes around the sun, right? These two are really close to each other. In a few million years, they might spiral into each other and sort of coalesce. But it's a double star where the stars are egg-shaped because they are almost touching. They're interacting, so they're whirling around each other every couple of days. But you can't see it with a telescope. So how do we know this? How we know it is exactly the same as the tornado example down here, because one star's we're off in this direction. One star's spectral lines are coming towards us, and the other star's spectral lines are going away from us. So we see the star exhibit red shifts and blue shifts over a period of 4 days. We can watch it happen, and so we know these things are orbiting each other just based on the Doppler pattern inside those spectral lines. So if we go back, what we really see, if we look at these spectral lines for Spica, is we see these lines make a little dance. They'll go blue shift, and then they'll go red shift, and then they'll go blue shift, and then they'll go red shift. So they dance around with a period of 4 days, and so we can tell that those are actually orbiting stars. Very, very cool. All right, we'll see some examples of that next week as we go along.